Quantum computers don't fail because the physics is wrong. They fail because they're drowning in errors, millions of them every single second. And the fix nobody saw coming didn't come from a physicist. It came from the same company that makes graphics cards for video games. For years, the story around quantum computing has been about qubits. More qubits, better qubits. Longer coherence times, bigger, flashier machines with names that sound like they belong in a science fiction script. But there's a much quieter story running underneath all of that. One that almost never makes headlines, and it's the story of why quantum computers, even the good ones, still can't do anything genuinely useful yet. That story is about errors, not bugs in the traditional sense, not software glitches you can patch with an update, but a constant, relentless noise baked into the very fabric of how quantum information exists. And in April of 2026, on what the industry calls World Quantum Day, Nvidia released something that attacks that noise problem head-on. It's called Ising, and depending on who you ask, it's either a clever engineering trick or the missing piece that finally makes fault-tolerant quantum computing feel within reach. Let's start with why this problem even exists, because understanding it is the key to understanding why Nvidia's announcement matters so much. A classical computer, the one in your pocket or on your desk, stores information as bits. Each bit is either a 0 or a 1, nothing in between, and that binary certainty is incredibly stable. You can flip billions of these bits a second, and the chances of a random error creeping in are vanishingly small, especially with all the error correction built into modern hardware. Quantum computers work on a completely different principle. Instead of bits, they use qubits, and qubits can exist in a superposition of states, a blend of 0 and 1 at the same time, until they're measured. That superposition is exactly what gives quantum computers their theoretical power. It lets them explore multiple possibilities simultaneously in a way that's simply impossible for classical machines. But that same property is also their greatest weakness. Superposition is fragile. It's disturbed by heat, by stray electromagnetic fields, by vibrations, by literally anything in the surrounding environment that interacts with the qubit even slightly. Physicists call this decoherence, and it happens fast. We're talking about timescales of microseconds to milliseconds before a qubit's delicate quantum state collapses or gets corrupted. Now imagine trying to run a calculation on a machine where the individual components are quietly failing at that pace, constantly, everywhere, all at once. That's the reality of quantum hardware today. Even the most advanced quantum processors in the world experience an error roughly once every 1,000 operations. That might sound rare, but stack up the number of operations needed for a genuinely useful calculation. Something like simulating a new drug molecule or breaking modern encryption, and you quickly realize that uncorrected errors would make the output meaningless within moments. This is why quantum error correction exists, and it's also why quantum error correction has been one of the 2 or 3 hardest unsolved problems in the entire field for over 2 decades. Here's how it works, at least at a conceptual level. Instead of relying on a single physical qubit to represent 1 unit of quantum information, engineers spread that information across many physical qubits arranged in a redundant pattern, most commonly something called a surface code. Think of it like a checksum system, but vastly more complex, because you can't just check whether the information is right or wrong without accidentally collapsing the very superposition you're trying to protect. So instead, the system continuously measures indirect signals called syndromes that hint at where an error might have occurred without ever directly measuring the protected quantum state itself. Then, and this is the critical part, a decoder has to take those syndrome measurements and figure out, in real time, what error most likely happened and how to correct for it. And it has to do this within the coherence window of the qubits themselves, which, remember, is measured in microseconds. If the decoder is too slow, errors pile up faster than they can be corrected, and the whole system falls apart before it produces a useful result. For years, the gold standard tool for this decoding task has been an open-source algorithm called pyMatching. It's based on a mathematical technique called minimum weight perfect matching, and it's been maintained and refined by the quantum software community as the reliable, trusted baseline that most research groups build on. pyMatching works. It's accurate, it's well understood, but it's also a classical algorithm running classical computation. And as quantum processors scale up toward the thousands or millions of qubits needed for truly fault-tolerant computing, the decoding workload scales right along with them. At some point, the decoder itself becomes the bottleneck. You can build a bigger, better quantum chip, but if your classical decoding hardware can't keep pace with the error correction demands of that chip, you've built something that looks impressive on paper but can't actually do useful work. This is the exact problem Nvidia decided to attack, and their answer wasn't a new qubit design or a new kind of quantum hardware at all. Their answer was artificial intelligence, layered directly on top of the classical GPU infrastructure they already dominate. It's a strange kind of full-circle moment when you think about it. The company best known for rendering video game graphics and training large language models is now positioning itself as essential infrastructure for the quantum computing revolution, not by building qubits, but by building the AI brain that manages them. The announcement is called Nvidia Ising, named after a foundational mathematical model from physics that dramatically simplified how scientists understand complex interacting systems, which feels like a fitting namesake for a project trying to simplify one of the most complex problems in modern computing. Nvidia describes it as the world's first family of open-source AI models built specifically for quantum computing, and it arrives in two distinct pieces, each targeting a different bottleneck in the path toward useful quantum machines. The first piece is called Ising Calibration. To understand why this matters, you need to know that before a quantum processor can even run a single useful operation, it has to be calibrated, meaning every individual qubit needs to be precisely tuned so it behaves predictably and consistently. Historically, this has been an intensely manual process, requiring skilled physicists to painstakingly adjust control parameters, run diagnostic tests, interpret the results, and repeat that cycle over and over until the processor is stable enough to use. It's slow, it's tedious, and it requires deep specialized expertise that not every lab or company has in abundance. Ising Calibration is a 35 billion parameter vision language model, trained specifically to read the kinds of experimental measurements and diagnostic plots that quantum physicists generate during calibration, and to infer, on its own, what adjustments need to be made. When paired with an autonomous agent, Nvidia says this system can cut calibration time from days down to hours. That's not a marginal improvement. That's the difference between a research team running a handful of experiments per month and running several per week, which compounds dramatically over the course of a research program. What's genuinely surprising here is how Nvidia chose to prove this model's competence. They introduced a new benchmark called qCalival, specifically designed to test how well an AI system performs on quantum calibration tasks, and according to Nvidia's own reported results, Ising Calibration outperformed some of the most capable general-purpose AI models available at the time, including systems from Google and OpenAI on this specialized quantum task. Now, it's worth being clear-eyed about this kind of claim. It's Nvidia's own benchmark, measuring performance on Nvidia's own specialized use case, and comparisons like that always deserve a healthy dose of scrutiny rather than blind acceptance. But even with that caveat, the underlying point stands on its own. This isn't a general chatbot awkwardly repurposed for physics. It's a purpose-built model trained specifically on the kind of data quantum experimentalists actually generate, and that specialization appears to translate into a real, measurable performance advantage on the exact task it was designed for. Then there's the second piece of the family, and this is the one carrying the headline number that's been circulating everywhere, Ising Decoding. This is the part that directly tackles the real-time error correction bottleneck we talked about earlier, the one where a decoder has to keep pace with error generation inside the coherence window of the qubits. Ising Decoding isn't one model, it's actually two variants of a compact three-dimensional convolutional neural network, each optimized for a different priority. One version is tuned for raw speed, the other for maximum accuracy, and Nvidia lets researchers choose the trade-off that fits their specific hardware and use case. These aren't massive models by AI standards either. The smaller, faster variant sits at around 900,000 parameters, and the larger, more accurate variant comes in at roughly 1.8 million parameters. For comparison, that's a tiny fraction of the size of the large language models most people interact with daily, which tells you something important about the nature of this problem. It's not about scale in the traditional AI sense. It's about specialization, precision, and speed under extremely tight timing constraints. So how does it actually perform? According to Nvidia's benchmarking, when the faster Ising decoding model is paired with the existing pyMatching algorithm as a kind of pre-processing and correction pipeline, the combined system runs up to 2.5 times faster than pyMatching running on its own, while also delivering meaningfully higher accuracy in identifying and correcting the errors that occur. In more specific technical testing, using Nvidia's own GB300 class GPU hardware running at reduced precision formats optimized for speed, the company reported achieving just over 2 microseconds per correction round, translating to roughly a 2.25 times speedup over the baseline approach, along with more than a 50% improvement in what's called the logical error rate, which is essentially the measure of how often the corrected, protected quantum information still ends up wrong despite all the error correction machinery running underneath it. And when they projected forward to a larger cluster of these GPUs running at even more aggressive precision settings, their model suggested the fastest configuration could push decoding rounds down to roughly 1/10 of a microsecond each. To put that in perspective, that's edging closer to the kind of speed where the classical decoding infrastructure genuinely stops being the limiting factor, and the physical qubits themselves become the primary constraint again, which is exactly where researchers want the bottleneck to sit. There's another detail buried in the technical reporting that deserves attention because it speaks to something beyond raw speed. Nvidia claims their decoding models require roughly 10 times less training data than comparable approaches to reach a useful level of performance. In the world of machine learning, data efficiency isn't just a nice bonus, it's often the difference between a technique that's practical to deploy across dozens of different quantum hardware configurations and one that only works well on the specific system it happened to be trained on. Quantum processors vary meaningfully from lab to lab and company to company in their noise characteristics, their qubit connectivity, their physical layout. A decoding approach that needs enormous quantities of hardware, specific training data to work well, is inherently harder to generalize. A model that can reach strong performance with a fraction of that data is far more likely to become something the broader industry can actually adopt and customize for their own machines, rather than something that stays locked to a single research group's specific setup. Now, none of this exists in a vacuum. Nvidia didn't just drop these models onto GitHub and walk away. They built an entire ecosystem around them. The Ising models integrate directly with Nvidia's existing Q platform, which is the company's software framework for hybrid quantum classical computing, essentially the bridge that lets quantum processors and classical GPUs work together within the same computational pipeline. They also connect with something called NVQ-Link, a hardware interconnect Nvidia introduced roughly 6 months earlier, specifically designed to let quantum processing units and GPUs communicate with the kind of low latency that real-time error correction actually demands. Without a fast physical connection between the quantum chip and the classical hardware doing the decoding, none of the speed improvements in the AI models themselves would matter, because the bottleneck would just shift to the communication link instead. So this release isn't really a standalone product. It's the latest piece of a much larger strategy Nvidia has been building for a while now, positioning itself not as a quantum hardware company, but as the essential classical computing layer that every quantum hardware company needs to plug into. And critically, Nvidia made a deliberate choice to release these models as open source, publishing them on GitHub, on Hugging Face, and through their own developer platform. Alongside the models themselves, they shipped what they're calling a cookbook, a set of practical resources covering fine-tuning, quantization, and inference workflows, plus specific recipes for integrating these tools into agentic automation pipelines, research papers detailing the underlying methodology, and benchmarking data researchers can use to validate the claims themselves, rather than just taking Nvidia's word for it. This openness matters strategically. It means individual labs and companies aren't locked into a black box. They can take the base models and fine-tune them on their own hardware's specific noise characteristics, adapting the general framework to their particular qubit architecture, whether that's superconducting qubits, trapped ions, neutral atoms, or something else entirely. That flexibility is a big part of why the early adoption list reads the way it does. And that adoption list is genuinely impressive, spanning the full spectrum of the quantum computing landscape. On the hardware and commercial side, companies like Atom Computing, EeroQ, Conductor Quantum, Inflection, IonQ, and IQM quantum computers are already integrating these calibration tools into their workflows. On the research side, institutions like Academia Sinica, Fermi National Accelerator Laboratory, Harvard's Paulson School of Engineering and Applied Sciences, Lawrence Berkeley National Laboratory's Advanced Quantum Test Bed, and the United Kingdom's National Physical Laboratory are all listed as early users. Companies like QCTRL, which specializes specifically in quantum control and calibration software, are also on board. When you see a list that includes national laboratories, elite university research programs, an international metrology institute, and multiple commercial quantum hardware startups all adopting the same underlying tool within weeks of its release, that's a meaningful signal. It suggests this isn't just a marketing push aimed at generating headlines. It's addressing a real shared pain point that the entire field has been struggling with simultaneously, largely in isolation from each other, until now. So why should any of this matter to you, especially if you're not a quantum physicist or a hardware engineer? Here's the honest answer. Quantum computing, despite decades of hype and billions of dollars in investment, still hasn't produced a single unambiguous real-world application that outperforms classical computers on a genuinely useful task at meaningful scale. Every few months, there's an announcement about quantum supremacy or quantum advantage, and every time, the actual value of the demonstrated task tends to be narrow, specialized, and mostly academic. That's not because the underlying physics doesn't work. It's because the engineering challenge of keeping enough qubits stable and error corrected for long enough to run a genuinely complex, useful calculation has been staggeringly difficult. Error correction has consistently been named by researchers across the field as one of the 2 or 3 biggest bottlenecks standing between where quantum computing is today and where it needs to be to matter economically. If Nvidia's approach genuinely delivers a 2.5 times speed up in decoding, combined with meaningfully better accuracy and dramatically reduced calibration time, that's not a minor efficiency gain. That's potentially years shaved off the road to fault-tolerant quantum computing, the point where these machines stop being fragile laboratory curiosities and start being tools that can solve problems in chemistry, materials science, cryptography, and optimization that are genuinely beyond the reach of classical computers. There's also a broader strategic story here worth sitting with for a moment, because it says something about where Nvidia sees its own future. This is a company whose stock market valuation has been built almost entirely on the artificial intelligence boom, on selling the GPUs that train and run large language models. Quantum computing, by contrast, has historically been viewed as an entirely separate technological frontier, running on completely different physics, different hardware, different expertise. But Nvidia's bet with Ising, and with the broader Q2Q and NVQLink ecosystem surrounding it, is that quantum computers will never operate in isolation from classical computers. Instead, the future looks like hybrid systems, where quantum processors handle the specific narrow tasks they're genuinely good at, while classical GPUs handle everything else, including, crucially, the real-time error correction that keeps the quantum side functional in the first place. In that vision, Nvidia doesn't need to win the race to build the best qubits. It just needs to make sure that whichever company does win that race is running its error correction and calibration on Nvidia hardware. That's a remarkably clever strategic position. It sidesteps the enormous uncertainty and risk involved in quantum hardware development, where it's genuinely unclear which qubit modality, superconducting, trapped ion, photonic, or neutral atom, will ultimately prove most scalable, and instead bets on something almost certain to be true regardless of which hardware approach wins. Whoever wins will still need massive amounts of classical compute sitting right next to their quantum processor. And Nvidia wants to be the default answer to that need, the same way it became the default answer for AI training infrastructure. There's also a data center angle to this story that deserves its own moment of attention, because it's easy to think of quantum computing as something happening in a physics lab far removed from the massive server farms powering today's artificial intelligence boom. That separation is starting to disappear. As hybrid quantum classical systems become more common, the classical side of that equation increasingly means racks of GPUs sitting physically close to the quantum processor, connected through low-latency interconnects like NVQLink, running continuously to handle calibration and real-time decoding. That's a workload profile data center operators are going to need to plan for, and it's a fundamentally different kind of demand than training a large language model. Training runs can often tolerate some latency, some scheduling flexibility, some queuing. Real-time quantum error correction cannot. It has to happen within the coherence window of the qubits, measured in microseconds, every single round, without exception, for as long as the quantum processor is running. That means dedicated, always on GPU capacity, sitting adjacent to quantum hardware, held in reserve specifically for this purpose, rather than shared across a general compute pool the way most AI training infrastructure operates today. For data center operators and cloud providers, watching the quantum computing space from a distance, wondering when it might become commercially relevant to their infrastructure planning. This is arguably the first concrete signal that the answer is sooner than most timelines assumed. It's no longer a hypothetical future workload. It's a specific, benchmarked GPU-bound task with published performance numbers, an open source implementation available today, and a growing list of research institutions and companies already running it. Whether that translates into meaningful near-term revenue is still an open question, since the number of organizations operating quantum hardware at a scale requiring this kind of continuous GPU support remains relatively small for now. But infrastructure decisions tend to get made years ahead of the demand curve, and positioning itself early as the default classical backbone for an emerging computing paradigm is exactly the kind of long game Nvidia has played successfully before, most notably with its early investment in the software ecosystem surrounding its GPUs, long before artificial intelligence became the use case that made those investments so valuable. It's worth pausing on the specific technical framing of the AI models themselves too, because there's something almost poetic about the naming choice. The Ising model, the mathematical concept these AI systems are named after, originally came from statistical physics nearly a century ago, describing how magnetic materials behave when countless individual particles interact with their neighbors in simple, local ways that somehow produce complex, large-scale behavior. It became one of the most studied and influential models in all of physics precisely because it showed how simplicity at the small scale can generate genuine complexity at the large scale. There's a certain symmetry in using that name for an AI system designed to manage the complex, emergent behavior of thousands of interacting qubits, translating the chaotic, high-dimensional noise of a quantum processor into something a classical computer can interpret and correct in real time. Of course, it's important to stay grounded and avoid getting swept up in the hype cycle that surrounds nearly every quantum computing announcement. The benchmarks Nvidia has published are, for now, primarily their own internal results, measured on their own hardware, using their own chosen comparison points and testing conditions. Independent, third-party verification across a broader range of quantum hardware platforms and noise conditions will be essential before the broader research community fully accepts these performance claims as universally applicable rather than optimized for a specific, favorable testing scenario. Quantum error correction is also a notoriously difficult field to benchmark cleanly because performance can vary enormously depending on the specific code distance being tested, the physical error rate of the underlying hardware, the precision format used during inference, and a dozen other variables that can be tuned to present results in the most favorable possible light. None of this means the claims are wrong. It just means healthy skepticism and patience for independent replication are the appropriate response, the same way they should be for any single company's self-reported benchmark, regardless of how impressive the numbers look on a slide. Still, even with that appropriate caution, the direction of travel here is hard to dismiss. Quantum computing has been stuck in a frustrating pattern for years, where impressive milestones keep getting announced, but the actual gap between laboratory demonstration and genuinely useful, economically meaningful computation keeps stubbornly refusing to close. Error correction and calibration have consistently been identified by researchers with no commercial stake in Nvidia's success as two of the most significant obstacles standing in the way of that gap finally closing. Watching a major infrastructure company throw its considerable weight, engineering talent, and hardware advantage behind solving exactly those two problems, and then choosing to release the resulting tools openly rather than locking them behind a proprietary wall is a meaningfully different kind of signal than another qubit count announcement or another quantum supremacy demonstration on a narrow academic benchmark. It suggests the field, at least in Nvidia's read of it, is entering a phase where the bottleneck is shifting from raw quantum hardware capability toward the classical infrastructure surrounding it, the calibration, the control systems, the error correction pipelines that make noisy, fragile qubits behave like something reliable enough to build real applications on top of. Whether Ising ends up being remembered as the moment that genuinely accelerated the timeline to fault-tolerant quantum computing, or simply as one useful tool among many that incrementally chipped away at a problem that ultimately required years more work regardless, is something only time and independent verification will settle. But the underlying signal is clear and worth paying attention to. The company that quietly became indispensable to the artificial intelligence boom by selling the compute that trains and runs every major AI model is now making a calculated, well-resourced bet that it can become just as indispensable to the next major computing paradigm, not by building the quantum chips themselves, but by building the AI-powered classical infrastructure that makes those chips actually usable at scale. If that bet plays out the way Nvidia is positioning it to, the story of how we finally got useful quantum computers might end up looking a lot less like a triumph of exotic new physics, and a lot more like a triumph of extremely well-applied artificial intelligence, running quietly in the background, correcting millions of errors a second on hardware most people already have sitting inside their data centers right now.